Hello everyone, my name is Junyong Yang, coming from Wuhan University. Today I'd like to introduce my paper entitled Scalable Time-Range Higgs Query on Temporal Graph. Let's first look into the motivation of this paper. Discovering community or cohesive subgraphs from temporal graphs has great values in many application scenarios. For example, in applications such as anti-money laundering, we would like to search communities like K-cores that contain a known suspicious account and emerge within a specific time interval, like the FIFA World Cup. The issue here is that the user typically do not know the exact time interval of the target. Actually, if we do know the exact time interval, an online decomposition is already efficient enough. Motivated by this, it is more reasonable to assume that we can only offer a flexible time interval and need to induce cores from all its subintervals. That's why we aim to generalize the historical query, which is proposed recently, by allowing the resulting K-cores to be induced by any subinterval of a given interval, like flexible versus fixed. And the historical query can be seen as a special case of our problem. For example, in this figure, the historical query under 1.8 will only return the largest core. However, our temporal query will return 4 cores, circled by different colors. To deal with TCQ problem, we propose an efficient algorithm called TCD algorithm. And then we develop multiple pruning techniques to accelerate the process. So firstly, let me introduce temporal code decomposition as a basic operation on temporal graphs, which is derived from the traditional code decomposition on ordinary graphs. The TCD operation consists of 2 steps. The first step is called truncation, which removes temporal edges with timestamps not in the query interval. Namely, this step induces the projected graph of the temporal graph. The second step is called decomposition, which iteratively pairs vertices with degree less than k, and the edges linked to them together. So for example, in this figure, we show the procedure of TCD operation that induces the temporal 2 core over 5/6 from the 1/2/6. In the first step, 5/6 edges marked by dashed lines are removed by truncation, and this will result in the decrease of degree for the 3 vertices, V5, V7, and V8. And in the second step, the decomposition will appear V7 and V8, since their degree is no longer larger or equal to 2. And finally, the remaining graph is the temporal 2 core over 5 and 6. Based on the above TCD operation, we can now have TCD algorithm to address TCQ. In general, the TCD algorithm enumerates each subinterval of the query interval in a particular order, so that the temporal K-cores of each subinterval can be induced decrementally from the previous one, rather than from the original graph or the projected graph. The figure here shows the TCD algorithm for finding temporal 2 cores of interval 1.8 on the example graph. We can see that each arrow represents a TCD operation, and clearly the TCD algorithm largely reduces the computational overhead compared with the inducing each temporal K-core independently. That's because for most induced temporal K-cores, a number of vertices and edges have already been excluded while inducing them. And actually, the underlying insights of the TCD algorithm is that it eliminates the intra-core redundant computation. Compared with the baseline algorithm developed by PCHC index, the TCD algorithm conducts a decremental procedure in which each vertex is peeled only once, and each edge is also removed only once. Therefore, the TCD algorithm is well implemented in physical level, achieves more efficiency than the baseline algorithm, even though it does not need any pre-computed index. So next, let me introduce the optimization techniques for TCD algorithm. In a nutshell, we directly prune subintervals without inducing their temporal K-cores if we can predict that the temporal K-cores are identical to other induced temporal K-cores. So for example, as shown in this figure, we can see that the temporal K-cores induced by 4.8 and 4.7 are identical. To achieve this, we need to propose a new key concept for static time interval, treated as TTI. The TTI, generally, the TTI refers to the critical interval, whose shrinkage will result in the change of temporal K-core structure. And the formal definition of time interval is that it is the type of interval that induces an identical temporal K-core of the query interval. But the challenge here is that how to predict which subintervals induce identical cores. So now let's introduce the detail of the pruning techniques. The insight here is that these three pruning rules eliminate the intercoincident commutation. The first rule is called pruning on the right. Consider the schedule illustrated here. For each row, the cells are enumerated from top to from left to right, row by row. In each row, we anchor the start time and let the end time decrease. For example, when the interval 3.8 is enumerated, it has TTI as 3.6. Since 6 is less than 8, the POR is triggered, and the two intervals followed will be directly skipped. And similarly, the POU will skip a lot of cells below the current row. For example, here, when the interval 1.6 is enumerated, since 1.6 induce temporal K-core with TTI 2.6 and 2 is larger than 1, then all 5 intervals from 2.6 to 5 until 2.2 will be skipped, since they are guaranteed to have identical TTI as the cells from 1.6, 1.5 to 1.2. And the similar procedure is also conducted for the pruning on the left side, or POL. And to efficiently implement the proposed method, we also devise a non-data structure called temporal edge list, shorted as TEL, to represent an arbitrary temporal graph. In a nutshell, the temporal edge list actually preserves a temporal graph in a three-dimensional list, namely the source list, the destination list, and the time lists. On the right side shows a partial TEL of the example graph. For example, the source list and the destination list here. Let's look at the edge V5, V7, and with timestamp 2. And since it has a source node V5, it is linked in the source list V5. And since its timestamp is 2, it is linked in the time list 2. And similarly, the edge V1, V3 with timestamp 1 is linked in the destination list v3 and the time list 1. And by utilizing the temporal edge list, now the TCD procedure becomes simply some pruning operations on the TEL. For example, this figure illustrates an example of using the temporal 2 core of 4.5 from that of 3.6. By representing cores in the TEL, the edges are going to be deleted and marked in red color. We can see that the procedure is actually a stream of edge deletion, while TEL will maintain the interest to retrieve the remaining edges. As for environment, to evaluate the efficiency of our algorithm, we firstly select 20 random valid queries, and the results are shown in the column chart. Clearly, the ODCD runs significantly faster than the TCD algorithm, and the TCD algorithm also runs significantly faster than the baseline algorithm. And we also conduct other 2 experiments to further evaluate the stability and the scalability of the OTCD algorithm. And the results shows that the running time of the OTCD algorithm are pretty stable, and the running time of the OTCD algorithm is also not sensitive to the length of the query interval, which means it is scalable. And finally, for the case study, we did several real temporal K cores on DBLP and U2, and the results are shown here. With more concrete information, we can infer the change of all those research interests or affiliations. And on the right side, we show a community that grows extremely fast. And such usages of TCQ will definitely facilitate applications such as recommendation, disease control, and etc. And here is a brief conclusion of our work. And that's all. Thank you.